This is the first video on thermochemistry, the scientific study of heat that is released or absorbs during chemical changes. We measure energy in a number of different ways. This energy readout shows expended energy in an exercise routine in calories. The SI unit, however, is the joule. The joule is 4.1 times larger than the calorie. From a recent investigation, citric acid and sodium hydrogen carbonate reacted. The reaction was spontaneous. It generated a gas, which is carbon dioxide, and the temperature of the solution that surrounded the reactants went down. Therefore, the chemicals reacting had to absorb energy from the water. The water molecules slowed down, and then that enabled the products to be formed, including the rapidly moving carbon dioxide molecules that escaped as bubbles. The reactant molecules broke up, and when they reassembled into products then, the products had higher energy than the original reactants did. This is how we could symbolize this. Your reactants here on the left, citric acid and sodium hydrogen carbonate. The reaction absorbed energy, and the product energy was higher than the reactant energy. This is called an endothermic reaction. Products have higher energy than reactants in endothermic reactions, and the surrounding water temperature goes down because energy comes from that water and goes into the reactant molecules to make the reaction happen. In the second reaction, magnesium reacted with hydrochloric acid to form hydrogen gas and dissolved magnesium chloride. The reaction was spontaneous. It generated hydrogen gas. The solution temperature, the water surrounding the reaction, went up. So the chemicals were releasing energy to the water in the course of making products. The water molecules then were forced to speed up. The kinetic energy went up as the reactants released energy to the water. Thus the reactant molecules broke up, and when they reassembled into products like hydrogen, the products had a lower total energy than the original reactants. Here's our symbolic language. The magnesium and hydrochloric acid reactants lost energy, becoming the hydrogen and magnesium chloride products. In exothermic reactions, the products have lower energy than reactants, and the surrounding water molecules get a higher kinetic energy, so the surrounding water increases in temperature. This is an interesting diagram that is made of energy and temperature in a closed system. If you don't let energy in or out of a system, then the total energy remains the same. Potential energy is stored energy inside the particles of matter. Kinetic energy is energy that is expressed in either vibrational or translation or rotational motion. Heat possesses the potential to transform and transfer energy, and we know that heat moves from the higher temperature object to lower. Temperature is a measure of particle movement. It's a measure of average kinetic energy. Here is an exothermic process. This is a useful diagram. In an exothermic process, you have potential energy that is stored in the molecules of the reactants, and a small amount of kinetic energy expressed in the water around. After the reaction, the potential energy in the reaction, in the products that have been formed, is smaller than of the reactants. The kinetic energy in the water that surrounds it is higher, and the temperature is higher. In an endothermic process, however, before the reaction, the kinetic energy of the surrounding water is higher than it is afterwards, and the temperature goes down as energy is transferred from the water to the energy of the molecules, the reactant molecules, and the reactant molecules then, after the reaction, have a higher potential energy than the reactants before. So product energy in an endothermic reaction is higher than reactant energy. However, in both cases, the sum of all energies is the same before and after. Here's another analogy that some folks like to use. A lake has potential energy, and before the spillway is opened, all of the energy, water energy, is potential. After the water has been allowed to flow down the spillway, however, the kinetic energy of the water now has taken up some of the original potential energy. As more and more water flows down, the kinetic energy becomes faster and faster, higher and higher. The potential energy of this water is much lower now, and after it hits the bottom, all of the energy is kinetic, and relative to the surface of the lake, there is no more potential energy available to turn, say, into electricity through an electric generator. Let's talk heat transfer. It can take place as chemicals react. In a system like you see here, where you have a nested styrofoam cup to provide insulation and give us a place for a reaction to occur, energy will be transformed from potential energy to kinetic energy, and that's measurable as a temperature change. Temperature is a measure of the average kinetic energy of a substance. If two substances are at the same temperature, then they have the same kinetic energy. Molecules move around and collide, and the faster ones give energy to the slower ones. So eventually this energy will be transferred to the surroundings by conduction. Now, since the solution that surrounds the reaction is now warmer, it is not perfectly insulated. So if you don't have perfect insulation, you will lose heat to the surrounding, say, air. So let's look at an investigation that involves temperature. If you take two identical volumes of water at two different temperatures and measure the temperatures in two different styrofoam cups, then mix them and find the new temperature, what do you predict the temperature will be of the mixture? Stop the video and think about that. Write your answer down and let's check. The result, if you did the reaction, it's actually a physical change, you'd find that the temperature was right between the warmer and the colder temperature. And so what's happened is, in our kinetic energy of the warm water, the molecules that were moving faster collided with the slower ones. The slower ones sped up, the faster ones slowed down, and they ended up with the same kinetic energy and the same temperature. Heat transfer can be by direct contact. We just talked about that when the water is mixed. Molecules run into each other. By convection, if you take a heater, it'll heat the air, and the air can then warm, say, food above it, a convection oven, or radiation, as in your microwave oven. When you turn that on, microwaves actually heat up the food by changing the orientation of the water molecules, making them move faster, and the water actually is what cooks the food, by making the molecules in the food move faster. And of course, we're appealing now to our old first semester, energy is equal to Planck's constant times the frequency of the electromagnetic radiation. It's important for us to distinguish between system and surroundings whenever we're talking about heat transfer. The system is the chemical reaction. The surroundings, everything but what's the chemicals in the chemical reaction. Delta E, the change in energy, is the final energy minus the initial. If energy comes out of the system into the surroundings, we give that a negative sign. If energy goes from the surroundings into the system, we give that a positive sign. Chemists always work with the energy of the system. We're not so much interested in what's happening in the surroundings. Delta is the Greek letter that means change. So delta T means a change in temperature. If the temperature goes from 20 degrees Celsius to 40 degrees Celsius, what's delta T? It's plus 20 degrees, final minus initial. Enthalpy is a measure of the internal energy in a system. You cannot measure it directly. You have to measure from the surroundings. A change in enthalpy, delta H, can be detected by a change in temperature of the surroundings. If the total enthalpy increases, delta H is positive. In this case, the reaction has absorbed energy, and the surroundings, the temperature has probably gone down. If enthalpy decreases, delta H is negative, and the temperature of the surroundings has probably gone up. This happens in either physical or chemical change. Here's a summary. In an endothermic process here, the enthalpy is increasing and delta H is positive. In an exothermic process, enthalpy is decreasing and delta H is negative. In a chemical reaction, the energy of reactants can be greater than that of products. Delta H then is negative, and energy has flowed downhill. The reaction is exothermic. If the energy of reactants is less than the energy of products, then delta H is greater than 0. Energy has had to have been pushed into the system to make it happen. The reaction is endothermic, and this is how we show that process. Final thing, in a chemical reaction, the molecules that react have to have enough energy to break the old bonds. That energy is called activation energy. And then, as you can see, there's an exchange of atoms, new bonds are formed, and that generally gives off energy. So all reactions start with an energy input and end with either energy being produced, net energy produced, or net energy absorbed. In order to react, molecules must then run into each other. In our reactions, when the citric acid and sodium hydrogen carbonate reacted, they did so without an apparent addition of energy. And so did the magnesium and hydrochloric acid. How did that happen? Where did the energy come from? Think about that. It appears that there must have been enough energy in the chemicals in the water to start the reaction, and in the case of the citric acid and sodium hydrogen carbonate, it even kept it going. The temperature of the water surrounding, of course, went down. There was enough energy in the water to keep the reaction going. This is a symbol of how we do this. We add the activation energy to the energy of reactant, energy of product diagram you've already seen. Delta H is still the change products minus reactants, but we've now added a little hump here showing that you have to actually add energy to get a reaction started. Is this an exothermic or endothermic reaction? It's exothermic. How about this one? Enthalpy of products is greater than reactants, so delta H is positive. This then is an endothermic reaction. And then from this reaction profile, calculate the change in enthalpy, delta H for the reaction. This is something that you might see on a test.